Large language models are pretty incredible, but we all know they have this issue where their knowledge gets stuck. It doesn't update.
And worse, sometimes they just make things up, confidently stating incorrect information. That's a real barrier to trusting them for certain tasks.
Right. Which brings us to this interesting new approach called ZeroSearch. The idea is to help LLMs find information better, but without using a live search engine.
Yeah, the researchers behind it are trying to get around a couple of big problems. One is the unpredictability you get when training with real search results. The quality varies wildly.
And the other is cost, I imagine. Training these things with reinforcement learning must mean hitting search APIs constantly.
That's it. The API costs can become, well, substantial, really substantial.
Yeah. So for this deep dive, we're looking at the paper that introduced ZeroSearch. Our mission, if you will, is to get under the hood, understand how it works, and figure out its potential advantages.
Sounds good. So the core concept is pretty novel.
How so?
Well, ZeroSearch actually uses one LLM to pretend to be a search engine for another LLM that's being trained.
Okay, an LLM simulating search, how do they make that work?
It involves a supervised fine-tuning stage. They take an LLM and specifically train it to act as a retrieval module.
Hmm.
The clever part is it learns to generate both useful documents and deliberately noisy or unhelpful ones in response to a query.
Huh. And how does it learn what's useful versus noisy? Is it just random?
No, not random. The paper says they use logs of actual user interactions with real search engines. They specifically look at query document pairs and differentiate between search attempts that led to correct answers versus those that went off track.
I see. So it learns from real-world examples of successful and unsuccessful searches.
Correct. And they use careful prompt engineering during this fine-tuning. The prompt includes the original question and the known answer, guiding the simulation LLM to generate either a document that helps answer the question or one that seems plausible but is ultimately a dead end.
So you end up with an LLM that can generate fake but realistic-looking search results of varying quality. How does the main LLM, the one learning to search, cope with potentially bad information?
That's where their curriculum strategy comes in. It's quite smart. During the reinforcement learning phase, they don't just hit the policy model with noisy documents right away.
They ease it in.
Sort of. They progressively degrade the quality of the simulated documents. It starts mostly helpful and gradually becomes noisier.
How do they control that degradation?
They use a probability function. The paper calls it pi, which dictates the chance of the simulation LLM generating a noisy document in any given training step.
And this function uses parameters. I saw PS, P, IM, and B.
That's right. PS is the starting probability of noise. P is the ending probability. I is the current training step. M is the total number of steps. As I gets closer to M, the probability of getting noise increases, following a curve determined by that B parameter, which defaults to 4.
Okay, so start easy, gradually get harder. What's the benefit of doing it that way?
The main benefit is stability and effective learning. The policy model, the one learning to search first, gets to grips with the basic task structure, like how to format a search query using the special tags, when the simulated results are mostly reliable.
It learns the ropes first.
Then, as its reward signal improves and it gets better, the task gets harder because the simulated documents become less reliable. This pushes it to develop more robust strategies for evaluating information and deciding if it needs to search again.
Makes sense. Learn the basics, then build resilience. So the reinforcement learning itself, it happens entirely without a real search engine, right? How does that work?
Fundamentally, the RL objective is to train the policy model, which they call PA, to maximize its expected reward. It takes an input question X, interacts with the simulation LLM, PA, whose parameters are kept fixed, and generates thoughts, searches, and answers.
And there's a reference model and a reward function involved too.
Yes. Pref, the reference model, is often used in RL setups like PPO to keep the policy from diverging too wildly. And RORF is the reward function that scores the final answer. But the crucial point is that Pref, the simulation LLM, handles all the retrieval. No external API calls needed during this RL phase.
So it's a closed loop almost. An LLM learning to search using results generated by another LLM. You mentioned special tags. Tell me about the training template.
Right, they use a structured template to guide the policy model's interaction. It involves 3 tags: think, search, and answer.
How does that play out?
The model first generates text within think tags, sort of reasoning out loud about the question and what it needs. If it decides it needs external info, it formulates a query within search tags.
And then the simulation LLM provides the documents?
Correct. Based on that search query, the simulation LLM generates a document, potentially helpful or noisy based on the curriculum stage. The policy model then processes this document and eventually outputs its final answer within the answer tags. It might loop through think search multiple times if needed.
It forces a kind of structured reasoning process. Think, maybe search, then conclude. Why enforce that?
The idea is that this structure encourages a more methodical approach. It separates the planning or reasoning step from the information gathering step and the final answer generation. This can make the model's process clearer and potentially more reliable.
Okay, structure for clarity. Now, how do they reward good performance in this simulation? What makes a good answer?
They use the F1 score as the primary reward metric. It measures the overlap between the words in the model's generated answer and the words in the ground truth answer.
F1 score. That balances precision and recall, right? Why not something simpler, like just checking if the exact answer phrase is present?
They found that using a simpler metric like exact match could actually be counterproductive. Models might learn to just generate really long, rambling answers, hoping to accidentally include the correct phrase somewhere within it, a form of reward hacking.
So F1 encourages answers that are both accurate and reasonably concise.
That's the idea. It penalizes including lots of irrelevant words just as much as it penalizes missing relevant ones. Interestingly, they also note they didn't need a separate reward term to enforce the think, search, answer format. The models seem to pick that up naturally just from the training process.
Efficient. Okay, let's talk results. How did ZeroSearch actually stack up against other methods in their experiments?
The results reported in the paper are quite positive. ZeroSearch showed consistently strong performance across a pretty diverse set of question-answering benchmarks.
What kind of benchmarks?
They use standard ones like natural questions, NQ, trivia QA, and pop QA, which are mostly single-hop, meaning you usually need one piece of information.
Okay.
But they also tested it on multi-hop datasets like Hotpot QA, 2Wiki multi-hop QA, Music, and even Bamboogle, which require finding and combining information from multiple sources.
And it did well on both types.
Yes, it consistently outperformed the baseline methods they compared against, and perhaps more significantly, it also outperformed methods that do use real search engines, like a setup they call Search R1.
Wait, it did better than models using actual live search results?
According to their experiments, yes. That really highlights the potential of this simulation approach. It suggests that the controlled, curriculum-based simulation might actually lead to more robust learning than just relying on the often messy reality of web search.
That's a very interesting finding. Was this success tied to a specific LLM, or did it work across different models?
They showed it generalized as well.
Yeah.
The paper reports strong results using different model families. They mentioned Quen 2.5 and Llamosa 3, and across different sizes, from 3 billion parameters up to 14 billion. It also worked well on both the base pre-trained models and models that had already been instruction-tuned.
So the framework itself seems robust, not just a quirk of one particular model?
That appears to be the case.
Let's focus on that simulation LLM for a moment. How good was it at actually mimicking a search engine?
The performance of the simulation LLM itself was a key finding. They found that a fine-tuned 7 billion parameter model could simulate search results at a level comparable to using Google Search directly, based on the downstream task performance.
Comparable to Google Search. Wow.
And even more impressively, a 14 billion parameter simulation LLM actually surpassed the performance achieved using Google Search in their setup.
So a sufficiently large, fine-tuned LLM can be a better source of search results for training than the real thing, potentially.
It points in that direction, at least within this training context. They also drew a clear distinction between fine-tuning the simulator versus just prompting a base LLM to act like one.
Oh, how big was the difference?
Quite significant. The fine-tuned simulators were much better at capturing the nuances and, crucially, at generating useful versus noisy documents appropriately. Prompting alone didn't achieve nearly the same level of performance or control. And they also saw, unsurprisingly perhaps, that the larger simulation models were better at making that distinction between relevant and irrelevant simulated documents.
Size matters for the simulator, too. Okay, what about the dynamics during training? You mentioned the policy model interacts with the simulator. Did they look at how many interactions or turns happened?
Yes, they tracked the average number of interaction turns, think search answer cycles, during training. Initially, the number of turns actually dropped.
Why would it drop?
The thinking is that the model first learns to use the search format efficiently. It gets better at asking a useful question quickly, so it needs fewer attempts early on.
Okay, it learns the basics of searching.
But then, As training progresses and the reward score starts to climb, meaning the model is getting better answers, the number of interaction turns starts to increase again and then level off.
Why would it go back up if it's getting better?
Because as the model gets more competent and the curriculum makes the simulated documents noisier, it often needs multiple rounds of searching and thinking to piece together the correct answer, especially for those harder multi-hop questions. It's refining its strategy, learning when one search isn't enough.
So the increasing difficulty forces more sophisticated multi-turn strategies.
That seems to be the interpretation.
Did they explore different RL algorithms?
Is ZeroSearch tied to one specific algorithm like PPO?
They mentioned testing it with both PPO, proximal policy optimization, and GRPO, group relative policy optimization. Both worked, indicating the ZeroSearch framework isn't dependent on a single RL algorithm. They did note, however, that GRPO seemed to provide slightly more stable performance across the different models they tested.
Good to know it's flexible. What about that curriculum study? You said it starts easy and gets hard. Did they try the opposite?
They did. They ran a reverse curriculum study, starting with the highest probability of noisy documents and gradually making it easier.
And how did that compare?
The standard easy-to-hard curriculum significantly outperformed the reverse hard-to-easy approach.
So starting simple and building up really is better here.
The results strongly support that. It validates their curriculum design choice, letting the model build foundational skills before facing the full complexity of noisy information. Let's circle back to cost. You mentioned avoiding API calls. Did they quantify the savings?
Yes, the cost analysis is pretty compelling. They estimated the cost of deploying ZeroSearch, which is mainly the compute cost for running the simulation LLM on GPUs. They compared this to the projected costs of using a commercial search API, like SERP API, for the vast number of queries needed during RL training.
And ZeroSearch came out cheaper.
Considerably cheaper, according to their estimates. The paper highlights potentially significant cost savings. Plus, they suggest you could potentially reuse the same simulation LLM server for multiple training tasks simultaneously, which could lower the effective cost even further.
That's a major practical advantage. Did they provide any specific examples, like case studies of how the model actually behaved?
They did. They showed some interaction trajectories. One key observation was how consistently the policy model stuck to the think, search, answer format, even though there wasn't an explicit reward just for following the format. It shows the template structure works well.
And did the examples show multi-turn reasoning?
Yes. They included examples where the model clearly needed to issue multiple search queries, process the results, and integrate the information before producing the final answer, especially for complex questions.
What about the simulated documents themselves? Could you really tell the difference between the useful and noisy ones they generated?
Based on the examples they provided using the 14B simulator, yes, there was a clear qualitative difference. The useful documents consistently contained information directly relevant to answering the question, often including the correct answer snippet.
And the noisy ones?
The noisy ones looked plausible, perhaps touching on the topic, but they lacked the specific information needed or contained misleading details. It really demonstrated the control they achieved over the simulation quality via the fine-tuning and prompting.
Okay, let's try to wrap this up. If you were to summarize the key takeaways from this deep dive into ZeroSearch, what would they be?
Well, the core idea is that ZeroSearch offers a novel and seemingly effective method for teaching LLMs to retrieve information. It does this by simulating the search process using another LLM, bypassing the need for real-time search engines during training.
Right, and the big wins seem to be avoiding those potentially huge API costs and gaining much finer control over the training data, the simulated documents.
Well, absolutely. That control, implemented through the curriculum learning, appears to lead to more stable training and, based on their results, surprisingly strong performance, even compared to methods that use live web search.
But it's not entirely free, is it? There's still a cost involved.
That's the main limitation acknowledged. You do need the computational resources, specifically GPUs, to run the simulation LLM. So it shifts the cost from API calls to internal infrastructure. But the calculation suggests it's a favorable shift.
Okay, so here's something to leave you, the listener, thinking about. If AI can effectively train other AI to search within these controlled, simulated environments, what does that mean for the future? Could this lead to AI systems that are more self-sufficient, less dependent on the constant, costly, and sometimes unreliable connection to the live internet for their knowledge?